It gives me great pleasure today to introduce Professor Park. The Consumer Electronics Society from the IEEE and the Institution of Electronic and Information Engineers of Korea, the IEEE, collaborate very closely, and we have mutual understandings and agreements in place where we sponsor and support each other's conferences. And if you look at this conference here, I think, was it 47% of the papers are from Korea? With such a high number, you can sort of see how dominant Korea is as a force in the consumer electronics industry. So it's an honor for us to have the president of the Korean IEEE here to give us keynote speech. So I'll give you a brief background. Professor Park, he has a BS and an MS degree in electronics engineering from Seoul National University and a PhD from Stanford. And from 90 to 93, he worked at AT&T Bell Labs in the US on 0.1 micron CMOS characterization, and later at Texas Instruments. Currently, he's a professor at Seoul National University in Korea, where he's working on semiconductor research. And he has also spent time as a visiting professor at Stanford, his old alma mater. And how much is he? He said it has, to our knowledge, published over 1,000 papers, peer-reviewed papers, and holds quite an impressive number of patents, 95 Korean and 33 US patents. So that's quite an achievement. And of course, being in the academic world, he has chaired and has been on various committees and worked on various conferences, and he's currently also the IEEE section chair for Korea. So we have a very distinguished and accomplished keynote speaker today with Professor Park. So let's welcome him here.
Thank you, President Moser. Well, first of all, I'd like to thank Dr. Hase and the organizing committee members for inviting me to this wonderful conference to present my introduction to the IEEE and also some of my works. So the first third of this talk will be about the introduction to IEEE, which means the Institute of Electronics and Information Engineers. Well, some people joked about the name of our institute because it sounds I. So he joked about it as, well, are you Yes Men's Club? So I said, yes, indeed we are, because we are composed of all positive people. We are always saying yes about the possibility of the technology. So IEEE was established in 1946, long before the IEEE. And the mission was to promote the academic activities in the fields of electronics, information, and communication. So we have about 33,000 individual members, out of which about 5,000 are currently active, and we have about 200 corporate members, including Samsung Electronics, LG Electronics, Hyundai Motor Company, and SK Telecom. The major activities are very similar to other institutes, academic institutes. such as the publishing magazines and journals, and the, of course, holding conferences, workshops, and many seminars. So this is the organization of our institute, and we are composed of 6 societies, and we have about 30 forums, which is part of these societies, and we have 9 regions. So these are the some details of the societies. So the biggest society currently is the Telecommunication Society, and it contains actually 9 forums or research groups, including all the area of the telecommunications. And the second largest is the Semiconductor and Device Society, which includes 5 research groups. And the other one is Computer and Information Society, including 6 research groups. And the Signal Processing Society has 4. And the Systems and Control Society has 7 research groups. And the 6th society is Industrial Electronics Society. And in Korea, we have 9 regions. So Seoul does not have any separate region. Seoul contains only the main office of the institute, and there are other 9 other regions in Korea. And overseas, there are 3 regions in Japan, and USA, and Russia. And we'd like to expand afterwards. And we have many publications, but I'll like to introduce only 2 of them, which are international journals. The first one is called Journal of Semiconductor Technology and Science. Since Korea is very strong in semiconductor area, we started this publication in year 2000, currently indexed in SCI and the Scopus. And recently we launched another journal called SPC, Smart Processing and Computing, covering most of the computing and electronics. And we have a few international conferences, and one is called ITC CSCC, International Technical Conference on Circuit Systems, Computers, and Communications, which is jointly held with the AICE, the Japanese equivalent of IEEE, and the Thailand equivalent of IEEE is ECTI. And another conference is called ICIC, which will be held quite soon this year in Singapore. And also last year, we hosted the ISCE, which is the one of the important conferences in Consumer Electronics Society. And this ISOCC is another international conference, which is hosted by the SoC design group. And we have a quite strong relationship with the IEEE, especially with the Consumer Electronic Society. So every 3 years we make MOUs with the IEEE and also with the CE Society. And also we have this joint award with the IEEE, and we select the bright young engineers in this IT field. Also, currently we are trying to establish another conference, which might be called ICCE Korea, maybe starting from year 2016. So I like to have a strong collaboration with the CE Society for the setup of this conference. So that's about it for the introduction of the IEEE. And I'd like to change the topic, which is the research area of mine. And the title of the talk is the persistent memories, past, present, and future. And I'd like to show you this famous picture from Salvador Dali. And coincidentally, the name of this picture is The Persistence of Memory. And it is famous for these flexible watches, or jelly watches, we may call. And I think I don't really know the intention of the artist, but my interpretation is probably the electronics in the future will be based on the flexible hardware, just like these flexible watches in this figure. So I'll focus on this topic later in my talk. So, well, I think my main mission here is to entertain you during the lunch. So I prepared a few pictures from the movies. So I guess you all know this. Most of you know this. What this is. This is the motion picture Total Recall, which is the first version of the Total Recall. So, so in order to talk about the past, I just brought up this picture. And I'll mention what is the oldest memory. And probably the most, one of the oldest technology of data storage is the paper. And then I'll mention the magnetic memories, and then flash memories, and some other memories. So my talk is mainly about the non-volatile memory. So persistent memory means the non-volatile memory here. But in computer science, I think people have some slightly different idea about persistent memory. But here I'd like to use this persistent memory as to designate the non-volatile memory. And the reason why I use this word persistent is that the non-volatile memory is really persistent and will be persistent. So I believe the oldest memory in the universe is the DNA. Maybe you might not agree with that, but well, DNA is definitely memory, and it may be called read-only memory. Right? We cannot erase it, or we cannot actually change it. Well, it might be changed only by accident or random mutation. And the retention time is really long, probably tens of, well, billions of years, probably. And it has 2 bits, and as I mentioned, it's read-only. And the main function is basically 2. One is duplication or copy, and the other is signal transmission, right? So that, well, it acts as a program of all the functions of the biological entities. The speed is very slow, but since it all works massively in parallel, the overall speed or throughput might not be so bad. Right? And I guess the artificial storage was started with the paper, and it has quite long history, actually. So we know the punch tape was used for the weaving machines so that they can produce very delicate patterns in fabrics. And it started, it is known to be started in 1725. And it survived for a long time. And it was used for the computer memory, right, in the early stage. And it was still used, actually, until 1970s, I believe. And it was replaced by the punched card. And it has also a very long history, but eventually replaced by the other electronic or solid-state memories. And the major memories was the magnetic memory, right, after the paper memory. And the first magnetic memory was called drum memory because the ferromagnetic material was coated on top of the drum. And it was used from 1932. It's quite old. And then in 1949, the core memory, or magnetic core memory, was invented. And basically, it has a bunch of wires and then a bunch of crossing wires and then ferrite cores so that we can change the direction of the magnetic field and change the magnetization of the cores. And later, people invented magnetic tape, basically coating the magnetic film on top of the long strip. And then in 1954, the hard disk drive was invented, and it's still surviving. In 1970s, bubble memory, which is the moving magnetic bubbles, was introduced. And it seemed to show a very strong potential as the non-mechanical memory. But probably because of its name, it disappeared very briefly because of the DRAMs and the hard disks. And recently, the MRAM, magnetoresistive memory, was proposed, which is based on this spin valve containing the permanent magnet and the changeable magnet here, and the tunneling insulator in the middle of them. So using the spin valve, we can switch the current. And it also requires the excess field effect transistor. Another line of memories is called flash memories. And until very recently, we have been using this floating gate structure, which is based on this floating gate, polysilicon floating gate, and the control gate on top of it. So we can store the charges in the floating gate. And it has two varieties. One is called NAND, and the other is called NOR. And NOR is sort of dying now, and NAND flash is taking over, right? Almost all the flash memories now, because of the advantage in density. So we can incorporate a lot more NAND flash cells compared with the NOR flash cells in one chip. And there are also other memories, like ferroelectric RAM, in which we are using the ferroelectric material as the memory node, or phase change memory, where we are using the chalcogenate material as the memory node, and basically we are crystallizing it or amorphizing it by applying the electric field and the heat. And another memory is called resistive random access memory. And here it is, the mechanism is somewhat similar to this PC RAM, but in this case, we are usually forming filament inside the chalcogenate material or other normally insulating material. And by forming the filament, we can switch it on, and by reversing the current, we can switch it off. So it is a very simple mechanism, and it has a potential to probably to replace the flash memory later. So here is a chart that shows the overall trends of the memory. So on top, right, in terms of capacity, the hard disk and also the optical disk is on top. And then the flash memory is closely following at the moment. And the other memories are somewhat behind. I think only the resistive RAM, RM, is closest to the flash memory at the moment. And other technologies are still lagging in terms of the capacity. So they are used in niche, especially for higher speed, higher random access speed applications. And here's a comparison between the hard disk drive and flash memory. And well, still the hard disk drive has a lot higher capacity compared with the flash memory. But the rate of increase of the capacity is sort of slowing down recently because I believe the hard disk memory cell is reaching its scaling limit. But I think there are some advantage in terms of scaling in the flash memories. So the capacity or density of the flash memory is still increasing very fast. So probably at some point the flash memory will catch up the hard disk drive capacity. Probably within 10 years. So what is the present status of the memory? I'll mainly talk about the flash memory. And I believe the current floating gate flash memory is reaching its limit. So charge flash memory is introduced recently and applied to the three-dimensional stackable flash memory. So I'll compare the gate stacked array and the channel stacked array of the flash memories. So flash memory is really booming these days, and the memory business is really now into the consumer electronics area because almost all the people are using the flash memories, right, in some way. So currently, I believe the highest capacity secure digital memory card has 512 gigabyte capacity, and it is used for various purposes, such as mobile phones, cameras, MP3 players, tablet PCs, USB flash memories, of course, and the camcorders. Now, it seems like all these other equipments are converging into the smartphones. But in any case, the flash memories will be the main part of the mobile equipment. But the dominant flash technology, which is based on the floating gate NAND architecture, is reaching its limit. So one is the interaction between the floating gates. Because they are so close now, the capacitance is so large. So we cannot ignore the interference between the memory nodes. Another problem is the word line direction scaling. So since we are packing so many cells into the chip, now the space between the cells are so small that the electrode here is acting like a very sharp electrode. So the electric field concentration is introduced a very serious reliability problem. So in order to reduce interference between floating gates, people started to introduce air gaps, which is probably the last resort, right? Because the air has the lowest dielectric constant. But it cannot go forever, right? Since this space is so small, now we cannot form any air gap at all, right? We have reached that point. So now people are discussing a different scheme. So just eliminate the wrapping of the floating gate with the control gate so that we can reduce the cell size. In order to do that, we can use very flat floating gate and high copper material, high dielectric constant material. But we still have this serious problem of scaling limit in terms of the number of electrons. So according to this prediction, we are, well, now in this region, about 20 nanometer feature size. And in this feature size, there are only like 10, or at least maybe just a few tens of electrons in a cell. So if you want to use it for 3-bit cell, right, we need to divide it into 8 parts. So how many electrons are there in one level of the memory? Maybe just a few. So this causes a very serious trouble in terms of memory performance. So memory is really prone to error in this era. So in order to, we have to increase somehow the area, the effective area of the memory, especially the floating gate. So people came up with the 3-dimensional device idea. So by rolling up this planar structure into the cylindrical structure, we can increase the area, which is very similar to the nature. In the nature, right, the memory machine is the brain, right? And the bird's brain has very little crease. Right? So it is very smooth. So it has very smooth surface. But compared with that, the human brain has many creases so that we can increase the effective area. So this idea is basically the same. And in order to make these 3-dimensional structures, the floating gate is really a nuisance, right? Because it is metallic, and metallic material can be very easily have leakage, right? Because if we put charge in there, right, they can move around inside the floating gate, and they can leak out through some hole, right, some via hole or some through hole in the insulator. So the charge trap flash, which is based on the insulating memory node, is really favorable, especially if you're thinking about the 3-dimensional structure. So the charge trap flash is not very different from the floating gate memory. The if we just eliminate the floating gate from the conventional floating gate memory, flash memory, we obtain the charge trap flash or Sonos structure, right? Because we already had this O&O region. And since we eliminated the floating gate, the interference disappears almost completely. Also, as I mentioned, the leakage problem, right, especially for small floating gate, it disappears. Right? So only the local region, maybe less than nanometer, will be affected by the defects in the insulator. Also, by using this 3-dimensional structure, we can use the focus of the electric field. This is very well known, right? If you just think about the Gauss equation, right? Gauss law, the electric field near the center will be much stronger. And that's what we exactly need in the performance in the operation of the flash memory, because we program through this inner insulator, and the electric field should be strongest there. So people were thinking about using this charge-trap flash memory for a while, but they could not beat the planar memory, the floating gate memory, until very recently, right, in terms of cost and scaling the integration capacity. But recently, the Toshiba came up with this very interesting idea, which is basically stacking of the memories. So they put down a lot of polysilicon on top of each other, and then punch holes in it, and then plug it, right, with the ONO, and then the polysilicon, so that we can have this three-dimensional structure stacked up. So this bit cost is, this BICS stands for bit cost scalable structure, which does not reveal anything about the actual structure. And then this is the improved version of the BICS. And Samsung came up with the slightly different idea. Basically, the structure is similar, but they sort of changed the order of the fabrication process so that they can have metal gate and the charge trap layer later than the channel. But all these G-star, the gate stacked devices, share the same problem. The problem is if we stack up all these structures, the resistance of the channel increases. So we have to face with this series resistance problem. The current for the same bias voltage will decrease. So the operating condition will be more and more harsh than before, right? When there are less and less stores in this building. So eventually, if you stack up too many layers, you might have to increase, not decrease, the cell size, which is against the scaling trend. So maybe we can compare it with this case. Well, this lady is from the Karen tribe. And they use these rings in their necks, right, to be beautiful. Right? So, but the problem is these many rings, right, in order to increase their length of neck, weakens their neck. So, unfortunately, in this picture, she doesn't look very happy, right? Worrying about the case of the stacked array memories. Also, another problem in terms of scaling, right? It has all these memory area exposed, right, in the vertical dimension. So if you just turn it around by, say, 90 degrees, we can decrease the cell area significantly, at least half. So actually, we came up with this C-star idea, channel stacked array structure. And in this case, we can use the epitaxially grown channels very easily, so that we can we don't have to suffer from the channel resistance problem. And by some process, we can round the channel, since this is a single crystal. And this shows the characteristic. But it still has one serious problem, and that is the cell addressing issue. So let me introduce the problem. This is the G-star, the gate-stacked array, and we can easily address bit lines, in this case, by lithography, by patterning it. But in the case of G-star, we turned it around by 90 degrees. And we now have to access these bit lines sideways, from the side, not from the top. And since we have only lithography tools now, we don't have any workers in this small size who can work on the side of the structure. The addressing of the bit lines are very difficult. So this is one of the schemes we came up with. So we use these combinations of the word lines so that we can address each layer. And this is a scheme. I will not go through the details. Right. So since it's already past 1, I'll speed up my talk. So I'll talk about the future of the memories. So this slide is, again, from a movie, Beauty and the Beast. I guess you might not know this movie because this is a children's movie. And well, I think this picture really captures the future of the IT, including the IoT, Internet of Things, right? So in this movie, all these inanimate things, like cups and the clocks, right? Even candles, are originally people, right? And because of the black magic, they turned into the things. But still they can communicate, right? They can do most of the things human can do. And what we are expecting in the future in IT is something like this, right? And IoT is part of this thing. So we'd like to communicate with things just like we are communicating with the other people. And we also like to have the things to communicate with each other. So in order to do that, I believe the interface between the human brain and the things or IT equipments are very important. Could be in various forms. So in order to do that, probably you have to compare the human brain and the memory. And the memory element of human brain is synapse, which is the terminal of the neurons, and they connect the neurons together. So that is the communication channel. And at the same time, it is a memory cell. So I believe in the future, the electronic synapse will become very important. So I would like to mention about that briefly. So here's the some statistics about the brain, human brain. So there are about 10 to the 11th 100 billion processors called neurons in the human brain. And 10 to the 15th, this is quadrillion, right? Quadrillion synapses, which is basically memory element. And if we calculate the memory capacity, it is about 1 petabyte. So the current memory is still a very, very long way to go, I believe, right? Just in order to reach the human level memory. So that's why I think the memory should be persistent, right? There's a really long way to go for the memory. And another thing is the short-term and long-term memory. Currently, we have separate short-term and long-term memory. Right? The short-term memory can be compared to the DRAM. Right? The memory disappears if you just leave it there. So we have to refresh in DRAMs. But there are also non-volatile memories, such as flash memories. So there's, again, a very interesting movie called 51st Dates. I guess many of you have seen that already. And the heroine here is forgetting what happened yesterday, right? Because of the accident. So the hero, our hero, should refresh the memory every day, right? So the movie is called 51st Dates. So this is the case where the short-term memory is not converted to the long-term memory. Also, there's something called interconnection bottleneck between the microprocessor and the memory, right? In the current computing system. So here's the microprocessor and DRAM and the hard disk. And even though the microprocessor has a huge clock speed, still it basically accesses the DRAM just 1 byte per execution. And DRAM is much slower than the SRAM in microprocessor. So it uses it as a cache. And again, the non-volatile memory is much, much slower than the DRAM. And if we substitute the hard disk drive with the solid-state drive, the problem does not vanish. Well, it's much faster than that, but still it is much, much slower, maybe 1,000 times slower than the DRAM. But in human brain, right, the processors are working in a really slow speed. Right? It is roughly about 100 hertz. Right? If you compare the speed with the microprocessor, it is 10 million times difference. But in some area, the human brain performs much better than the computing system currently. And that is because of the architecture. Right? The memory is not separate from the processor. Right? The memory is residing right where there should be. They are residing in the interconnection between the processors, not in a separate remote place. So the memory is called synapse in human brain or in all neural systems. And they have very different signal transmission system and memory system. So one of the important area we can focus on is the building electronic synapse So, well, the neuron was usually compared with the logic gates, and synapse is compared with the memory cell. But in reality, neuron has much higher complexity and capability. So maybe you have to compare it with the CPU rather than a logic gate. And the synapse should be compared with the memory chips or memory module. So maybe a computer might be a better analog of the neuron, and router might be the better analog of the synapse. And some people compare the neuron to the universe because it contains everything. And maybe we have to compare the synapse with the radar, interstellar radar. But we have to achieve it with just one device or two. So this is the work we are doing in our lab. So we like to achieve the short-term and long-term memory in one transistor. And we know the mechanism already, right? By having impact ionization, we can generate the majority carriers in the channel so that we can implement the short-term memory. And by having this floating gate or memory node and then pouring these majority carriers into this region, we can have long-term memory. So at least in simulation, we achieved the short-term and long-term memory. And also, we achieved the spike timing-dependent plasticity, which is known as the main principle of the learning mechanism of the brain, just by one transistor. So let me conclude. Well, in the past, the magnetic memories were dominant memory, and hard disk was the ultimate winner. But recently, the scene is changing, so the flash memory is sort of taking over the hard disk drives. And in the future, maybe the synapse-like memories may play a very important role in neuromorphic systems. Thank you very much for your attention.
We're sort of running a bit short of time, but maybe we can have one question. Is there any questions from the audience? Yes, Richard.
Test.
Thank you for your review and roadmap of silicon technology and its application to understanding neural processes. What do you see as the role of software and perhaps the broad term, not programming, but teaching, learning to make the most of the synaptic devices you're describing here, please?
Well, first of all, I'd like to say that where is the software in the brain? I couldn't find the place where the software is stored. So probably the brain is achieving what the software is doing by flexible hardware. That's what I'm thinking currently. So my vision is probably the flexible hardware platform will be the next IT topic. And software, I think, should still have function in there, probably very high-level function. So probably we have to have very flexible hardware, and then we need to develop a software on top of that. That will probably reduce the power, because one of the reasons why we have still a very high power, right, compared with the brain, is we are using software too heavily. We are using currently the multi-purpose, omni-purpose processors in order to accommodate all the software commands. But probably that might not be the good idea. So eventually, we might have to have flexible hardware so that most of the things will be processed by hardware. And so software is on the highest level and then directing the flexible hardware. That way we can save a lot of energy and we can speed up all the processing. Because hardware, in theory, hardware should be much faster than the software, right? So.
Professor Park will still be around, so if you have any more questions, you can come and see him and talk to him. But on behalf of the Consumer Electronics Society, I want to show our appreciation for his excellent keynote speech and present him with this plaque.